Yeah, just wanted to thank you all for joining us today. This is our second webinar, and it's going to be about integrated assessment models because this is the first step in our modeling activities. And we also are networking with some projects who are using them in their activities. So we wanted to have this joint event to explain not only just an overview of how they work, but also how they have been using in different projects at European level. So we have representatives of not only in the HYDRA project here today, but also from Nevermore and Choice. So thank you to all the speakers for joining and giving the presentations. So we already wasted some time, so maybe we can jump right to the presentations. We are going to have an introduction on integrated assessment models, an overview of the WILIAM model, which is the one we and Nevermore project are using. And then we will have a presentation about the choice project and the integrated assessment models they are using. We are going to have a Q&A session at the end, but if you want to drop questions while you hear the presentation in the chat, then we are going to ask them at the end of all the presentations. I'm going to leave the word to Inigo, who is going to present the overview and introduction on integrated assessment models. So Inigo, the floor is yours.
Okay, thank you, Rosella. Hi, everybody. So we are having some technical problems. Cristina, you are going to share our presentation.
Can you please send it to me by email?
Okay. I thought, okay, one moment.
Is it the one on the HYDRA SharePoint? I can share it if you... Okay, so I will share it.
It's the same link for me and for Juan, who is also sitting here next to me.
Okay.
Okay, so next, just to start. So my presentation, I'm going to present two main topics. I'm going to start by a very general introduction to integrated assessment models. And then together with my colleague from CARTIF, Noelia, we are going to share an overview of the WILIAM model, which we are using in the HYDRA and the Nevermore projects. It's going to be a very general overview because we will see it's a very big model. So just to give you a general idea of the main goals and main differences with the relation to other integrated assessment models. Okay, so next. Okay, so, well, in general, before entering into the tool, because integrated assessment models are tools, I would like to speak a bit about the problem they want to address. So basically, they address two sides problem. One side is the environmental and sustainability, which probably is very well known to all the attendants of this webinar. We can illustrate this and sustainability with the concept of the planet boundaries, which here we can see the evolution over time, which are different dimensions of the Earth, which are very important that they are kept in balance and not so much disturbed, so the Earth system works properly. And there are things such, of course, climate change is one of the elements, but we have biodiversity, water, land use, pollution, etc. So you can see in this figure that these trends are worsening and accelerating. So this is a main worry. Even if integrated assessment models have traditionally been focused on climate change, their goal or their aim will be to tackle all these dimensions. So next one, please. And so we have on the one hand this environmental unsustainability, which is caused by the by how the industrial system works. It's a very linear system in which we have inputs, we process inputs, and we produce a lot of waste. And the paradox is that even if we are consuming a lot of resources and we are disturbing the global planet with our wastes, we are not even able to provide basic human needs to the global population. So as you know, many billion people in the world are lacking basic human needs such as sanitation or employment, education, etc. No? So I will say this is the main problem. Next one. So to analyze this type of global general problems, appear the concept of integrated assessment model. No? So these models have typically two spheres, the human system sphere and the natural earth system sphere, no? Because we are interested about studying the interaction between the two. In the human system sphere, we have dimensions such as economy, food, population, science and technology, energy. And in the natural earth system, we have all the natural elements, biosphere, we have oceans, we have the climate, water, etc. So because sustainability is multidimensional, no, we need this type of tools which represent different dimensions. So this is, in my view, the main point of these integrated assessment models. No? The key is the integration between these dimensions, and we can try to test different things. We can see where the current trends take us, what happens if we implement some policies, what are the risks of some policies or strategies. Also, we can measure some uncertainties, etc. Next one, please. So this is a couple of slides just to illustrate very visually the benefits of integration. No, in the previous slide we saw that there were some boxes, for example, called energy or economy. No, so as you know, there are many models which are only representing energy dimension, or they are only representing economy dimension. No, so can you 2 times click? Yeah. So when in this type of models, no, yes, like that. When in this type of models you introduce an input, okay, you obtain one output. No, this is an example, abstract example if you use a focus specific model. So next one. When you integrate with another module, and you can again click 2 times, what happens is that the interaction, only one interaction with one module, change the behavior of the system with the feedback. So you can see the blue lines is without the feedback, and the orange lines is with the feedback. This is a made-up example, but this we find in many cases when you integrate. You don't need a lot of complexity in terms of interactions between modules to get a different behavior of the model. Next one. Okay, and here I wanted to give you a bit fast overview of the historical developments of integrated assessment models. Is my, let's say, personal view. I think everything more or less started in the 70s because different happenings, different things happened this decade. We had the first UNEP, United Nations Environmental Program Conference in Stockholm, where for the first time there was an international setup to deal with global environmental issues. The same year was published the very influential and important Limits to Growth report, which showed that the current trends were totally unsustainable, and they also provided some ideas to break these collapse dynamics. Click, please. So, well, in the 70s, 2 things happened. There was a very fierce critique, and I would say unfounded, but this is, I don't have time to enter into this now, criticism of this report. And also there were the energy crisis with the oil shocks in the 73, 79, and so on. The price of energy increased a lot. So there was a motivation to build energy models to understand the energy problem. The OECD created the International Energy Agency, etc. So at the end of the 80s, when the climate change problem started to be important or recognized, the first models were these energy models of the 80s and of the 70s and 80s, which were coupled with a kind of emissions, concentrations, proto-climate models. And here we also have first IAMs. I wrote there DICE, range was more on pollutants, and image. And from the 90s, there was a full development of integrated assessment models in synergy, coordination with the IPCC process and the IPCC reports. As the IPCC was developing, so were also the models, which were increasing in detail and incorporating more dimensions, land, SDGs, etc. Okay, you can continue. Yeah, so they have evolved to become some kind of, let's say, standard. Maybe standard is too strong, but some kind of very well-established models for the evaluation of public policies. Okay, next. Okay, so you can click 2 or 3 times. Let's see the arrows. The idea at the end, conceptual idea with this type of models, I imagine most of you are familiar with this idea of donut, which merge the planetary boundaries with the social boundaries. The idea will be to move our scenarios or our future, our strategies, following the yellow line, no? In which we don't trespass the ecological ceiling and we respect the social foundation. And we identify potential trajectories which go outside of the donut. Next one. Well, here you can click several times because it's a figure with many animations, but basically it's just to explain how you can use this type of tools, because I mean, a model is just a set of equations, and you need to have some parameters, data to initialize them. So basically in integrated assessment models, because you have this comprehensive view of nature and humans, you need something that we call storylines or narratives about how do you think, or how would you want to hypothesize that the future will evolve. This will allow you to parameterize all the exogenous parameters of the model, which can be a lot depending on the type of model. And then you also need, of course, to do different types of hypotheses, structural hypotheses, parametric, etc. Then you have all the IAM running, and you get some results. And then the question is if the goals, I mean, it depends also on the type of scenario you are performing, because you can run a baseline scenario in which you want to more or less project current trends, or you can project alternative scenarios to try to test different policies. No? So the first question will be if it's a policy scenario, if the goals are reached, and if not, then you need to iterate. So iteration is at the heart of at least simulation IAMs, because you have also optimization IAMs, which optimize, and that's the end of story. But with simulation models, you need to do these iterations, which can be manually or automatic. Okay, next. Okay, and here I will link with WILIAM presentation. Maybe I'm going to skip this because we lost a bit of time at the beginning. And you can click, and I will start with WILIAM. Well, I don't know, Chair, if we want to have questions after each presentation, or we keep all the questions at the end. I guess
we keep them at the end.
Okay. Okay, so, well, in this general context of integrated assessment models that you have seen that there is a long history of decades, those familiar with IAMs know that there are many models, no? This is due to different reasons, institutional, methods, etc. Why we decided to create some years ago new models? Because WILIAM at the end is a continuation of the work we started with another IAM, which was called MEDEAS. Even if it's a different model, but the conceptual background is, let's say, similar, or the motivations are the same. So the idea is to have a model which has emphasis on the representation of potential biophysical limits. So the model is WILIAM within limits IAM, and interaction with socioeconomic constraints. So here I don't have, again, too much time for these details. We can go over that in the question if anybody is interested, but there are some key, but I still want to say briefly, yes, thank you, some things about this. So one of the critiques, classical critiques, is that the IAMs have a too simplistic representation of the economic process. You will see that we have a very complex economic module. And the fact that these economic modules are very simple don't allow to properly model the interactions with the biophysical dimensions. Also in IAMs, there are some key dimensions which are missing, typically demography, society, materials. The energy is usually assumed as very, very high availability, which is not is discussed or debated by some branches of biophysical economics, for example. They are neglecting future energy investments, so everything related with net energy analysis and ROI. And also, they don't address properly, or well, this is improving over time. To be fair, the challenges of 100% renewable systems. Okay, now we can continue. Okay, this is a screenshot of the main intermodule links, the model. So, well, here you see that we have different modules and we have different levels of integration. The highest level of integration is between energy, economy, materials, and land. Well, we are working on most of these interactions or also on new ones. Maybe you can also continue. Yes, so we just released a version of the model at the end of September in the link that was in the previous slide. It's available in GitHub. Also, there is some documentation in the wiki. And in terms of software, we are programming this in system dynamics software, which is called Benzene, which is proprietary software, but it's possible to run the models with a freeware. Everything is explained when you download the model. Okay, so some general characteristic of the model. So the time resolution is quite small. I'm talking for the typical integrated assessment models. We can call it quasi-continuous. The model is multi-regional. That means we have different regions that interact between them. In terms of methods, we are combining very different methods. I mentioned system dynamics methods for these feedbacks between dimensions. We have also input-output analysis in the economic module. We have LCAs in materials, econometric analysis also in economic module. And one of the challenges that we are addressing is this consistency between monetary and physical dimensions. So the model is policy optimization, no optimization. Is very big, as I mentioned before, but we have made a very big effort to have a modular structure. So the idea is that anybody interested into using the model can run parts of the model isolated in a, let's say, easy way, technically easy way. This gives a lot of powerfulness to the analysis. So it's an open source model. We have documentation and it is in development. Next one. Okay, so now I continue with another part of my presentation, which is, together with Noelia, we are going to give a very fast overview of the different modules, okay? So I'm going to cover first, very quickly, demography and social modules. These modules are amongst the, let's say, less developed in the model, but still they have very interesting features. For example, in the demographic module, we have all the cohorts. We have a differentiation by gender, by age, and so on. So we have this aging population change. We can compute things such as dependency ratios, and we can also model exogenously at the moment hypotheses about migration, how this will affect the results of the world model. In terms of society module is basically a module with indicators. When the model is run, we get some outputs, and we want to understand these biophysical and monetary results. What do they mean for people? So we have indicators about inequality. I will explain that in the economic module we have, for most of EU countries, different households types. So we can compute Gini within countries and also within regions. Then we have a basic education module, and in terms of development, we are calculating the HDI, Human Development Index. Okay, yes, we can go to economy. So economy is very, very complex module. Click again for some very basic features. So for those familiar with economic method, this is a dynamic econometric multi-regional input-output model. As I mentioned, it's a simulation, so no optimization or equilibrium assumptions, which dominate integrated assessment models. Typically, it has high detail. Besides the 60 types of households in EU countries, we have government, we have 62 industries, and 35 regions. So you can see there are different colors, no? There are different sub-modules within the module, no? We have a representation of labor, capital, production. We have also a financial sphere for households, which I think is not here, but is in the model. Okay. So that will be an overview of economy. Next one. Yes, so this is the energy module, which basically the energy module should be understood as a energy system model, but it is linked with the rest of modules. It's a module that we have developed from scratch and that has very interesting features. First, to connect with the economic demand and also to get biophysical limitations, for example, for materials in terms of oil, gas, uranium, coal, and with land use for biomass. And we also get, I don't know, for example, CO2 prices from economy, which dynamize many things. So basically, we have a representation of the full energy transformation chain with a lot of detail. You will see later in the presentation of Juan, because this was also needed for integrating hydrogen. I mean, it's needed because you need to have this granularity for replacing the processes. And from this, we calculate the emissions also in point of views with a lot of detail. Okay, maybe next one. In terms of materials, we include in materials two things: fossil fuels, uranium, and minerals, the main minerals, the base minerals, copper, aluminium, iron, and nickel. So basically, we have a very hard integration of supply-demand dynamics of fossil fuels with the economic module. We have uranium availability constrained by maximum depletion curves. And then we have, and this is related with net energy assessment for ROI, the bottom-up requirement of 22 types of critical minerals for the moment for mainly renewable technology, solar PV, solar CSP, wind, onshore and offshore, and electric batteries for transport or also stationary. And I think this is it. Yes, so this is it from my side. So I will give the floor to Noelia so she can continue with the description of the land, water, and climate modules. Thank you for your attention.
Thank you, Inigo. Noelia, are you able to share? Do you want me to continue sharing?
I can share. Can you see my screen now?
Yeah.
Oh, okay. Perfect.
Yes.
Okay. Well, as Inigo has explained, I'm going to talk about the environmental part of WILIAM that is composed by the land and water and climate modules. These, as the others, are interrelated with the rest of WILIAM, with society, energy, economy, with several variables, and in particular, the land module has different features. On one side, we have the demand of products to the land from several aspects. From one side, from economy, for the demography, on the part of diets and land products demand. In addition, we have policies for diet change, so we can evaluate the effects of a change in diets on land, on the demand of land products. Also, we have links with energy in the land module. So energy demand, also land products, for example, from biofuels, from forest biomass, land for the deployment of solar PV on land. And in addition, if there is not enough land area for these uses, there is like signals that are sent to energy to stop the deployment of new renewable energy. Also, in the land module, we have a part where the demand of land products are like allocated between different regions, because as explained by Inigo, it's not just global level, but we have also global regions. And also between different uses. So in this pool, all the land products are allocated between uses and regions. And also there is an options to try different policies regarding global crops distribution or priorities of uses. You prioritize food, for example, above energy, or the opposite. Also, we have in the land module the land uses part. In this part, all the land products that are demanded is distributed between different land uses, depending on the production of each land use, of course. And also, we can put or try different policies regarding land protection, afforestation, urban density that affects also the land area that is occupied. In addition, we have a specific sub-modules for grasslands, forest, and crops and yields for these specific uses to provide with specific policies options. For example, in grassland, it's possible to apply policies regarding carbon capture. That is a very good, has a high potential for carbon capture, this land use type. Also, forest, it's possible to apply policies of forest management that affects also the carbon emissions and the good availability. And in the crops and yields, it is possible to apply different policies for agricultural management. All this is linked with emissions. So we have emissions calculated endogenously in WILIAM regarding the land use sector. So we have emissions from the land uses, the forestry part, and also the land use change, of course. And even for agriculture side, we have emissions from livestock. For example, the change of diets affects the number of animals, and this affects emissions. And this is also in WILIAM. There is a policies of management of the carbon in soil, and also policies of management of the manure from the livestock. And this is feeding the climate. So climate is fed by emissions from land use, but also climate affects the land module, climate change impacts. So there are climate change impacts here that affects forests, crops and yields, and also sea level rise. The water module, on the other hand, it receives information from society demand, from economy demand, and also for agriculture. And there is an option to try policies regarding the prioritization of human consumption and also of water efficiency. A water module has also not only the demand sub-module, but of course the availability sub-module that is affected also by climate, different scenarios of climate that affect water availability. And also there is a signal to the energy module regarding the stress, if there is water stress, how this affects to hydropower. The climate module, on the other hand, it has like several parts. On one side, we have the emissions that it fed the climate module. These emissions, the emissions that are calculated endogenously on WILIAM, are the CO2, the methane, and nitrous oxide emissions, or are calculated. So we have the land use sector emissions from land use change and forestry, and also agriculture. We also have from industry and waste endogenously, more stylized, more simple than the others, but we also have endogenous calculations, so in line with our scenarios. And also energy are very developed in terms of emissions calculations. The rest of emissions from other type of gases or greenhouse gases are from exogenous, these emissions, and then this is transformed into the concentration of these greenhouse gases on the atmosphere, because in WILIAM we have each cycle model, and then this concentration is transformed into total radiative forcing that allows WILIAM to calculate the increase in temperature. So in WILIAM it's possible to calculate the increase in temperature at global level, and also some impact effects like ocean acidification, and also sea level rise. And also wanted to just name recently some improvements that we have regarding climate change impacts and adaptation, because as I have said, we have a climate model that allow us to create new climate scenarios. So we have climate change impacts modeling in demography and society modules, in particular effects of heat stress and cold stress and mortality rates. Also climate change impacts on capital stock and labor productivity, and also in the land part, as I have said before, impacts from sea level rise, how this impacts the agricultural land area occupied by the water, and on crop yields also we have these impacts included. And now I also going to present, because we wanted to put into place how WILIAM is improved in different projects. Already Inigo has mentioned that WILIAM started with another model, what is the same. So the beginning was with MEDEA's model within the MEDEA's project, and then it was a lot improved in the locomotion project and was renamed as WILIAM, as we know today. And after that, we have several projects where WILIAM has been applied and at the same time improved, specifically in Rethink Action. Rethink Action is more focused on land-based policies and mitigation and adaptation policies, and therefore if there is adaptation, also we have work into climate change impacts, but focus on the biophysical, on the land-based part. And then in IAM Compact is more about application of these models, and we also improve WILIAM in several aspects, but intercompare with other integrated assessment models that were part of this consortium, just ended 1 month ago or two. And then we have now the two projects that are going to be presented today, that is Nevermore and HYDRA, that they are still in development. The first one they are going to present more in detail, but are focused on climate change impacts and adaptation, while HYDRA is focused on the hydrogen-based policies and their impacts evaluation on, or from a sustainability perspective in different impacts on different systems. So would be a little bit the WILIAM model in different projects. And now I think I give the floor to the next speaker.
Yeah, thank you, Noelia. And also Inigo for your presentations. One I can share for you, because I guess you have the same problems as Inigo.
Thank you.
Okay.
I think he can share because I can see it's his permission, but
okay, we will do it like with Inigo. Hi all, my name is Juan Manuel Campos from the University of Valladolid. In this talk I will talk about the current progress within the HYDRA project in implementing the hydrogen futures into the WILIAM model. Go next, please. Okay, click one. No, go to the previous. Okay. The objectives of this talk are twofold. First, I'm going to present the methodology for modeling the hydrogen sector in WILIAM and the progress we have currently achieved. and I am going to show also some preliminary global scale results. The focus will be on the energy aspects as they constitute the core of the modeling work. Go to the next, please. The methodology we have followed for the implementation of hydrogen in WILIAM consists of several steps. First, we have selected the hydrogen technologies and sectors, and then we developed a detailed representation that includes the theoretical framework, the process-based modeling, and parametrizations. These representations capture both energy and materials flow, as well as environmental aspects such as hydrogen leakage. Once complete, all components were integrated into the WILIAM model, forming what we call the hydrogen submodule. Go next. The submodel embedded within WILIAM interacts dynamically with the rest of the model. For example, the model provides to the submodule the information about the economic evolution, for example, and then the submodule calculates the energy and environmental implications of hydrogen in the system. Go next. On this slide, you can see a kind of graphical abstract of the hydrogen value chain we have implemented in the model. We have included a supply side, including fossil fuel-based processes as well as electrolysis. Hydrogen in the model can be used on site, but also can be commercialized prior distribution and storage stage. And we have also modeled hydrogen-based fuels production to be used as substitutes, direct substitutes of current fossil fuels. And on the demand side, we have modeled several uses, and we will go deeper to each of them in the following slides. Go next, please. And we have also, to the previous, sorry. On each stage of the energy chain, of the hydrogen value chain, we have also included the hydrogen leakage on each point of use. Okay, so we therefore estimate all the hydrogen leakage along the whole hydrogen value chain, because that's one of the objectives of the project. On the supply side, I'm going to go through each stage I mentioned before in more detail. On the supply side, hydrogen can be produced in our model through fossil-based processes. These are current routes for producing hydrogen today. These are steam methane reforming, which relies on natural gas consumption, and coal gasification, which relies on coal consumption. And as an alternative, we have modeled the electrolysis, which has the potential to be much cleaner to the previous processes, although it presents certain challenges, including lower conversion efficiencies and the use of scarce materials. Next. Pure hydrogen can be utilized to produce hydrogen-based fuels, as I mentioned before. We have modeled electrolytic-based methane production and electrolytic-based methanol production. These synthetic fuels have the advantage of leveraging existing fossil fuel infrastructure. So we only have to model the supply of these fossil fuels, and the uses rely the same as fossil fuel fuels. For all these hydrogen synthetic fuels, the process of producing these synthetic fuels requires CO2. So we need to, we have modeled the carbon capture and use processes in order to model the energy and environmental implications of this carbon capture. We have considered as CO2 sources industrial processes and product uses, industrial sectors, refining and coke, and direct air capture. Next. Regarding distribution and storage, e-methane and e-methanol can take the existing fossil fuel infrastructure, and pure hydrogen, on the other hand, can be distributed via pipelines and stored in compressed tanks. And for international trade of hydrogen, we have modeled transmission between regions by ship in the form of ammonia. And for all of these processes, we have considered all the energy requirements and energy losses that occur during these distribution and storage steps. Go next. And on the demand side, we have included current uses of hydrogen, which are the uses of hydrogen as feedstock in oil refining, ammonia and methanol manufacturing. And we have also modeled emerging applications of hydrogen, such as steel manufacturing, hydrogen use in passenger transport, and the use of synthetic fuels to meet demand for gaseous and liquid fuels. Additionally, CARTIF has modeled hydrogen for freight transport and for high temperature industrial process, which I think they will present after my presentation. Next. For the specific modeling of hydrogen as a feedstock, we have conducted an extensive data collection effort, since comprehensive and consistent global data sets on hydrogen remain scarce in the literature. And also, before the development of the full submodule in WILIAM, we have also carried out preliminary scenario analysis using a prototype hydrogen model, the results of which have been recently published. Next. Now I will move on to the results. First of all, we have defined for this webinar a set of socio-technical scenarios that serve as the inputs of the model. These include a baseline scenario and a green growth scenario without hydrogen, which is the second one, and 3 green growth scenarios with different levels of hydrogen deployment. In the low hydrogen scenario, we only consider the replacement of existing fossil hydrogen-based processes, and we have replaced it with electrolysis in the scenario. In the medium hydrogen scenario, we go a further step and include hydrogen use in steel production, the emergence of a hydrogen economy with a moderate commercialization of hydrogen, and the deployment of synthetic fuels to substitute final energy liquids and gases. And finally, the high hydrogen scenario, we assume a larger share of merchant hydrogen, international hydrogen trade across regions, and a higher penetration of synthetic fuels in the overall energy system. All these scenarios are applied at the global scale, and in order to obtain illustrative results for this talk, we have extended the simulation period to the year 2050. And the energy model operates under quasi-isolated conditions, with the exception of its link to economic output. So we have deactivated all the feedbacks with the other module in order to show the illustrative results. Go next. All these results I'm going to present you here are preliminary results, as we are still in process of validation. This first set of results are the share of final energy demand by fuel. You can see the baseline scenario, where the share of final energy by fuel remains nearly constant for each fuel. Under a green growth scenario, which is the second graph, we see a higher share for final energy of electricity and a reduction of shares in final energy liquids and gases. And in the hydrogen scenarios, both the electrification and hydrogen produced and the share of hydrogen increase. It is important to note that the most of the hydrogen produced in the hydrogen scenarios is not directly reflected in final energy consumption due to the way energy accounting is defined. However, its effects can be observed in other parts of the energy model, as we will see in the next slides. Go next. In the top left, you can see the total hydrogen production by scenario. rising from around 100 million tons of hydrogen that is produced today to over 1,000 million tons of hydrogen in the most ambitious case. In the top right, you can see the share of renewables in the electricity mix, which all the green growth scenarios reach about 80% of renewables, but in the most ambitious hydrogen case, the share of renewables decrease a bit. It reaches up to 75%. This is due to the depletion of renewable potential and the increasing curtailment of variable renewable energy sources, because the hydrogen deployment requires an extensive electrification. You can see in the right down the global electricity generation by scenario. We can see in an increase of about 130% of increase in the global electricity generation due to hydrogen deployment. So this massive electrification implies not only the depletion of renewable energy sources potentials, but also the increase of curtailment in power generation. We also estimate the electrolyzer capacity stock, which are the infrastructure needs in the top, in the down left, you can see the graph for the capacity stock, which reaches up to 10 terawatt of electrolyzers. Go next. In this slide, we show the primary energy supply by scenario. We see that under a green growth scenario, the primary energy supply increased a bit relative to baseline, while reducing the primary energy consumption of oil and natural gas. But when we include hydrogen scenarios, we see a massive increase also in primary energy, nearly doubling the results of the green growth scenario. This hard increase is due to all the energy efficiencies that imply all the hydrogen-based processes compared to the fossil fuel processes that in the final term are reflected in an increase in primary energy requirements. Go next. I'm going to show the last results regarding the emissions. On the left hand, you can see the CO2 emissions by scenario. The green growth scenario shows some degree of decarbonization relative to the baseline scenario. But when we implement hydrogen scenarios on top of the green growth scenarios, the additional decarbonization effect might be limited or even reversed, depending on the scenario. This outcome of increasing CO2 emissions is mainly driven by the indirect effects of low conversion efficiencies, extensive electrification, and the saturation of renewable potentials mentioned earlier. And on the right-hand side, we show hydrogen leakages along the whole hydrogen value chain, which are relevant, these leakages, because as you know, they contribute to radiative forcing, and one of the expected outcomes of the project is to estimate the radiative forcing of this hydrogen leakage. Go to the last slide of the conclusions. The model, the WILIAM model with the hydrogen submodule captures many demand and supply dynamics, both specific to the hydrogen sector and to the energy system. We have seen that the hydrogen deployment scenarios have very significant energy implications. We see a massive electrification, an increase in global system inefficiencies, leading to an increase in primary energy, and a difficulty of decarbonization due to indirect effects, such as these indirect effects are the depletion of price potential, curtailment, etc. And for the future work within the projects, we plan to refine scenarios and energy mix scenarios. and deepen into the implications of hydrogen scenarios on the other modules, such as the materials modules, the land module, etc. And that's all by my side. Thank you all.
Okay, thank you, Juan. Pablo, are you
Yes.
going to share? Okay.
I am sharing my screen. Okay. Okay. So I will continue the presentation from Juan, talking about the freight transport submodule that was developed for HYDRA project in WILIAM, and just give a brief overview of the whole submodule, and talking a bit about the results, the preliminary results that these scenarios give in this submodule. So the general structure, the freight transport submodule, is inside the energy module in WILIAM, and it's a model that disaggregates the output desired for freight that comes from the economy module, and it disaggregates into different transport activities inside of the submodule, and then it calculates final energy consumption of this freight transport activity that translates into energy and also into greenhouse emissions that are connected to the climate module, giving these feedback loops and these complex dynamics that Íñigo explained before in WILIAM. So the key features of the freight transport submodule are that it's able to disaggregate this transport demand, first by transport mode, and second by different powertrains for each transport mode. So it is able to disaggregate an important part of this general data and economy data for sectors, that allows this module to make calculus in a bottom-up strategy. So different data disaggregated that then aggregates into big results, and also can calculate the energy consumed and emissions for all of these types. Also, as we saw, this submodule is interconnected to use the endogenous data from WILIAM and save this global system dynamics in energy and economy modules with some feedbacks to the policies that we are going to apply in this submodule. As is important and embedded into HYDRA, some new hydrogen-based technologies for transport, mainly for freight transport, for trucks, for ships, have been parameterized to explore different decarbonization pathways based on hydrogen. And finally, the submodule is capable of applying for different policies. Transport mode shifting from some modes like road transport, trucks, to other other modes with less emissions, like train. Also, you can change the powertrain shares between internal combustion engines, electric powertrains using hydrogen, and also can apply improves on energy efficiency and reductions on emission factors for each of the modes of the transport modes and the powertrains that the model has. So we are going to see some preliminary results. For us, the key results are the CO2 emissions, the direct CO2 emissions for the freight transport, and they are shown in a cumulative way for the European Union. The different policies are applied for a global for the global spectrum, but we saw results for EU, and these are cumulative emissions from 2015 to 2050. There is a first scenario that is a baseline, and then 3 different scenarios. One with decarbonization but no hydrogen, one with a low hydrogen implementation, and one with a high hydrogen implementation. These parameterize the policy targets that are being considered in the EU and in global level for different for the policies that apply in this submodule. And then the first scenario ignores the policy targets from hydrogen. The second scenario uses the low lines preview for hydrogen, and the final scenario, the top lines, the most ambitious scenarios or targets for hydrogen. And if we see the difference in the cumulative emissions for these different scenarios, we can see that from the baseline, the decarbonization scenario reduces at 29% all the emissions, and then the hydrogen scenarios, the first one with a low implementation is able to reduce at 2% more than the decarbonization, basic decarbonization scenario, and with a high implementation of hydrogen that includes using powertrain technologies for transports in sea, for ships based on ammonia, or new trucks with internal combustion engines based on hydrogen, the cumulative emissions could be reduced by a 38%. And if we see the different policies in a more focused way, and we differentiate the effects that each policy has on the general combination in the decarbonization scenario, we can see that the most important is the improve of energy, the improve of the energy efficiency of vehicles, and the reduction related in emission factors that reduces a 17.4%. The mode shifting, the transport mode shifting is also important, reducing alone, being applied alone, almost at 12% of the cumulative emissions, and the powertrain share being applied alone is the less powerful, we could say, policy, but it's obvious that the combination of these three is the key factor that allows us to reduce the 29% that the decarbonization hydrogen, the decarbonization scenario with no hydrogen allows to reduce in the cumulative CO2 emissions. So this is more or less all. It's a brief overview, I know, but if you have some doubts, I am open to answer it.
Thank you, Pablo. So I guess we will have the last part from Noelia, right?
Yes, thank you. I'm going to share my screen. Now, can you see my screen? No.
Not yet.
Now, yes, no? Okay.
Yes.
Okay, in my case, I'm going to just put some examples of how land is integrated into HYDRA, or specifically the usefulness of the land module for HYDRA is to check the impacts of the hydrogen deployment of this part of land, of this module. In particular, there are different impacts of hydrogen deployment on land. Once they are direct, by installation of hydrogen supply chains directly, as for example electrolyzers, but others are indirect. For example, for the deployment of hydrogen is needed more solar energy PV associated that occupy land. And on the other hand, also there is a need of biogenic sources for producing synthetic fuels because it's needed CO2. The final objective of including in the analysis the impacts of land is to have the possibility to avoid potential negative effects of this deployment, to design policies for land use planning or land protection to avoid those negative impacts. These are some examples. These are just totally preliminary scenarios because no, they are not complete, but just to put as an example without checking the numbers. For example, here we have different integration of synthetic fuels in the system. This is represented by a share of final energy, gas and liquid, substituted by synthetic fuels. And there is like 3 levels. One is the higher penetration, another is the medium, and in the business as usual, that there are not any share of this penetration of synthetic fuels. As I have said before, this means that more hydrogen is in the system, and also that more synthetic fuels are in the system. On one side, for example, these are some impacts that can be quantified in the model, like the effects of of land occupied by solar energy PV. These are one of the indirect effects because, as I have said before, energy and land are connected in both ways in the WILIAM model, and so land requirements are fed to the land part, and also even there is like the possibility to model the scarcity, and it's possible to see how this affects, for example, in the business as usual with respect to a medium penetration of hydrogen regarding synthetic fuels to the higher penetration of share of synthetic fuels in the final energy. Also, we have included in HYDRA, although they are, as I have said, preliminary results, but we have modeled the production of the origin of CO2 to produce synthetic fuels based on hydrogen. As I have said, there are 3 potential sources to produce CO2. These are the carbon capture and utilization in industry, biogenic sources that comes therefore from the land module, and direct capture from atmosphere. In the model, what we do is first to prioritize the carbon capture and utilization when decarbonizing the industry, and then the rest of the CO2 needed comes from the 2 other sources. In particular, what we have done in HYDRA is to model 2 technologies in the part of land, biogenic sources to provide this CO2 from fermentation to produce bioethanol, because CO2 is a co-product, and bioenergy carbon capture and usage that is BCC2 technologies, which we think that they are the more viable in the future. So at the end, there is, like I have said, preliminary results because it's not all integrated, but it's possible in WILIAM to see how much biomass is needed, how much CO2 from biomass or biogenic sources are needed to produce these synthetic fuels. As I have said before, there were 3 scenarios. First is prioritize the CO2 that comes from industry for the carbon capture and utilization, CC2. And in these scenarios that are an example, just in the high scenario is the one that is not enough with this CO2 produced by this carbon capture and utilization. So we need or biogenic sources or to apply the direct air carbon capture technology that, as you know, is something novel now. And here is the CO2 produced, calculated from for the fermentation, the production of bioethanol as a co-product. And here is how in the higher scenario of HYDRA of synthetic fuels production, not all the CO2 is covered, of CO2 demand is covered, as an example of how William can calculate these potential problems regarding CO2 feedstock for some uses in the future, in future neutral scenarios. But just to comment again that are preliminary results, so it's just to see the futures that William will have. And well, these are from my side. I think HYDRA is the last presentation.
Yeah, exactly. Thank you, Noelia, and all the speakers. And just wanted to remind everyone that if you have questions, you can drop them in the chat, and then we are going to answer at the end of all presentations. And next up is the presentation of how William is using the Nevermore project. And Adrian, I guess this is your time to present.
Hi. Good morning or good afternoon, everybody. Let me share my screen. Can you see it now?
No. Yeah.
Yeah?
Yeah.
Okay, so yeah, welcome everybody. My name is Adrian from CARTIF, and today I'll introduce you our work within the Nevermore project. And let's start with the project itself. Nevermore mainly aims to deliver an integrated cross-scale assessment framework to evaluate climate impacts, risk, and policy options. And our work was mainly part of the Work Pact 3, whose focus is the improvement and development of the WILIAM climate model, which was explained before by Noelia. And we put particular emphasis on 2 fields mainly. First, the creation of high-resolution climate datasets that later fed the impact and risk assessments of the different case studies that are contemplated in the project, and also the improvement of the climate model itself in order to try to model and capture dynamics, impacts, and risk. The first point was mainly carried out by other partners, Democritos from Greece and Potsdam from Germany. So CARTIF, together with the UVA, has mainly focused on this last point, the improvement of the climate model. First, I would like to show how the workflow has been done. First, we started with the review of other models, global climate models and Earth system models. in order to identify potential climate features that WILIAM was missing, how they work, the inputs and outputs they require. Then after identify these interesting features, we created a list of potential improvements, and we try to create some criteria to prioritize them. Some of these criteria were the rationality, the feasibility to implement them into WILIAM, and also the importance and the impacts that these features could have both for WILIAM and for the NEVERMORE project. And finally, with this list of possible improvements, we implement them, those that were prioritized, placing special emphasis on the planetary boundaries and the tipping points. Well, here I put the definition of the planetary boundaries, but they were already explained by Iñigo in the first presentation. And as he said, there are 9 different planetary boundaries. Most of them are already, well, their thresholds have already been trespassed. And some of the planetary boundaries that were not addressed in WILIAM were or have been responsible for the UVA, while others have been for CARTIF. In our case, we have tried to implement the stratospheric ozone depletion, the ocean acidification, and the biogeochemical flow survey. Yeah, so starting with this first one, with the stratospheric ozone depletion, its definition is the gradual thinning of the ozone layer, which is mainly caused by the ODS, the ozone depleting substances, especially the CFCs and the halons. There are 2 indicators, the ozone concentration and the equivalent effective stratospheric chlorine or ESC concentration. And we chose the layer because it was the one that was most suitable for WILIAM, and its threshold is 3 parts per billion. This is the equation we have used to model it within WILIAM. And through this new implementation, we also were able to calculate the relative forcing of the ODS. These are...
Adrian, sorry, can I just interrupt you 1 second just to say that at 12:30, Sibyl will have to start her presentation because then she will have to leave, just to give
okay.
you some time constraints.
Yeah, okay. I'm gonna try to make it as fast as possible. Well, these are the results. As you can see, the trend is decreasing. So this planetary boundary is improving thanks to the Montreal Protocol. Second planetary boundary we modeled is the ocean acidification, which is the reduction of the pH because the ocean uptakes CO2. There are 2 indicators, the pH itself and the aragonite saturation state. The threshold for the latter is 2.75, and this aragonite is a calcium carbonate, which is part of many marine organisms. So it's really important for the ocean ecosystem. These are the 2 equations that you can use to calculate the pH and the aragonite saturation. And it's also interesting to note that the pH is associated with a tipping point, the coral reefs die off. And well, this is a structure we have included in WILIAM for this planetary boundary. And here you can see the results. In this case, both the pH and the aragonite saturation state are decreasing, so this planetary boundary is worsening. And this is the comparison between the current pH ocean and the threshold for the tipping point for the coral reef diode. And although at the beginning of the simulation, the pH is above the threshold by 2050, William says that it will be this threshold will be crossed. So it's really concerning for the ocean ecosystems. Finally, the biogeochemical flows. There are two, the nitrogen and the phosphorus. The indicators are for the nitrogen, the fixation, which is the transformation from the atmospheric nitrogen into reactive forms, whose threshold is 62 teragrams per year. And for the phosphorus is the inflow that goes from the rivers and coastal waters into the ocean. And the threshold is 11 teragrams. To model these two cycles, we have taken into consideration the inputs from agriculture, household, and industries that go to wastewater, and this wastewater is usually sent to rivers, and this way all these pollutants enter into the cycles. Well, here you can see the complex structure that has been added to William for the modeling. And here you can see the results. Although the units at the left side are different, you can see in the values below the charts. With the charts that both thresholds have been crossed. So even at the beginning of the simulation, the values are way bigger than they should be. So it's a very concerning problem. And apparently the phosphorus cycle is getting even worse in the future, while the nitrogen may improve by 2050. And this is all. Sorry for the pace, but if you have any question, you can do it at the end of the webinar. Thanks a lot.
Thank you, Adrian. So just to remind the next presenters that we have 7 minutes left.
Perfect. So, okay. I'm going to share my screen. Do you see it? Do you hear me?
Yes.
Yes.
Yeah, of course. So, hi everyone, I'm Daniel. I'm from the University of Valladolid, and I will continue to show the integration of planetary boundaries, as well as an example of the impact of climate change and integrated into WILIAM. This is a brief index, but we don't have time for it. So let us begin with the planetary boundary of land system change. This planetary boundary is based on the global extent of forest area compared to a reference value consisting of the original forest area. The change of forest area is estimated endogenously in the WILIAM model, but in the latest version of the model, factors have been added that adapt this area to its stage of conservation. For example, damage from forest fires, which involves a duration period, and damage from forest management have been included. This allows us to better apply it to the framework of planetary boundaries. Some preliminary results we can see that in the graph on the left, William's results show us a downward trend in global forest area entering into the high-risk zone by the end of the decade. The results match with the extract from the literature, for example, from the Planetary Health Check 2024. Another planetary boundary included is the biosphere integrity. This planetary boundary is based on the amount of net primary productions, NPP, consumed by human activities. The net primary production is the carbon extracted from the atmospheric CO2 and converted into biomass by vegetational cover. This latest version of WILIAM, under the framework of NEVERMORE, includes an estimate of changes in NPP at global and regional levels. It also estimates the amount of NPP consumed by human activities through harvested NPP, by grazing on grasslands, or land products by crops, for example, or groundwood extraction, and NPP gain or loss due to land use changes. This global human appropriation of NPP can be introduced into planetary boundary framework by comparing it with a reference value extracted from the literature. The preliminary results of this planetary boundary is shows an upward trend on the overall of the global human appropriation of NPP, placing us in the high-risk zone. This trend matches with the found in the literature, but with some underestimation. This can be adjusted in the future developments, so we'll keep working on it. Finally, of the planetary boundaries features, I will briefly show results for the planetary boundary of climate change. The concentration of CO2 in the atmosphere is estimated endogenously in WILIAM, and applying it to the planetary boundary framework, we see how we are situated in the zone of increasing risk, matching with the literature. Okay, it happens the same with the total radiative forcing, which is on the upward trend that places us well above the planetary boundary. To end my presentation, I will introduce one of the geophysical impact of climate change, that is wildfires on forest land. During the NEVERMORE project, we work with the ECMIP database, which provides us with projections of burnt area by region according to the temperature change. We integrated this into the model by applying the WILIAM temperature change that is endogenous. To adjust it better, we apply it to the historical burnt area extracted from another database, that is our whirling data. The result of this way, we have a first historical period that introduced the burnt area from forest records, and a second period that applies the projections. This is applied as a loss of forest area in other variables, such as those related to the estimation of NPP, for example, for the estimation of the status of land system change planetary boundary, or for other biodiversity indicators that have been integrated into WILIAM under the framework of NEVERMORE project. So I hope I'm being quick. So I leave you with my colleague Paola. Thank you for your attention.
Thank you. So Paola, you're up next.
Okay,
Just
yes.
keep it really brief.
Yes, I'll try to be as brief as possible. So hi everyone, I am Paola López Muñoz from the University of Valladolid, and I'm going to give you a quick overview of the climate change socio-economic impacts that we have included in WILIAM within the NEVERMORE project. So first of all, why is important to include endogenous climate change socio-economic impacts in integrated assessment models? Well, we consider that this is essential because it ensures to have internally consistent scenarios. This is that we can obtain this way GDP trajectories that already reflect the reductions caused by climate impacts. Nevertheless, the state of the art is characterized by the fact that most IAMs usually do not explicitly represent these impacts, and when they do it, they are often captured through highly aggregated monetary data functions that simplify the complex channels behind. So what we wanted to do in the NEVERMORE project was to enhance the WILIAM model by representing multiple endogenous climate change impact channels in a bottom-up manner. This means that we explicitly represent the impact channels. So as an overview, here we represent what we did, which was to include socioeconomic impacts through 3 different direct effects, which are the effects on infrastructures, capital, the effects on occupational health, labor productivity, and the effects on mortality. And by doing this, after we can observe the indirect effects in many other variables. So regarding data, for mortality, we modeled deaths from heat and cold stress using information from Breslin et al., a recent paper that provides regional country-based damage functions capturing the effects from temperature increase and mortality. And we included this in WILIAM by increasing the mortality rate, which in turn reduces population, and afterwards, since there are many interlinkages, population also enters in other parts of the model, as my colleagues present in previous slides. So, for instance, this also determines the level of available labor force in the economic module. Regarding the capital, we included damage by using information from this source for Cherry et al., which provides disaggregated data in terms of damages by sectors and different countries. And we derived different damage functions to represent the capital extra depreciation rate, depending on temperature, calibrated to represent the effects of heat waves, wildfires, and droughts. And this impact affects also the different variables indirectly in the model, such as the capital, the available capital, and also the investment needs, triggering many other dynamics in the economic module of WILIAM. And for labor productivity, we tried to represent the reduction in workers' capacity due to heat stress. We used information from different exposure response functions in the literature, and we also used data from ICNIP, which is a database which has a lot of information about impacts. And we derived some damage functions that captures differences by occupations, taking into account the level of exercise that the different jobs require under heat stress conditions. And we also have information depending on one or another source, and also by impact, by regions. Sorry. And these impacts are essential in the model because the labor productivity has a key role in determining the economic growth. So it also affects the level of employment, wages, prices, and trade dynamics. And regarding results, I will go very quick on this.
Sorry to interrupt you, Paola, but due to another commitment for Sibyl, we are forced to swap your presentations, so you can finish your presentation after hers. Sorry.
Okay, it's just 1 minute if you want me to finish right now, but what do you prefer?
Yes, because she has another commitment.
Yeah, please go ahead. I will keep mine short. Please finish.
Okay. Thank you very much. You can go on.
Okay, so very quickly, for a baseline scenario in which we have this temperature increase pathway, we can observe many different results, such as the effects of on mortality rates by regions, and depending on, we can observe the difference between hazards. We can observe the changes in mortality rates due to heat stress, but also to cold stress. For the capital part, we can see this is the global effect on the consumption of fixed capital, although we can also observe impacts by sectors and regions. For the labor productivity part, we observe, for instance, the indirect inflation effect, also depending on the type of the level of impact we introduce. And in final terms, in general terms, when we apply all the socioeconomic impacts together, we can see that the effects on GDP as an explanatory variable are very, very high, more than those that other integrated assessment models that use aggregated damage functions provide. So, well, these are more or less the examples we can have for this. And this is all from my side. Thank you.
Thank you, Paola.
Thank you. And we can finally have the last presentation from Sibyl about the CHOICE project.
Yes, thank you very much to the HYDRA Project for also inviting us. And I'm glad to hear so much about the WILIAM project and learn so much about it. And I know we are running late and I don't want to eat up anyone's lunchtime anymore. So I will try to be as brief as possible. But I also have to say, I will talk about 3 models we use in the choice project, not only one. So therefore it will be also a bit intensive, but that will be very brief. So for further information, please get in touch either with me or with my colleagues that I will share the emails about if you have any further questions. So there was a call, I think 3 years ago, about improving the integrated assessment models. And we heard a lot about integrated assessment models. So one weakness, only one of the several weaknesses found in the literature, is that they focus on techno-economic factors, techno-economic solutions for climate and sustainability problems. As you see in this figure that shows the main solutions and sectors covered by the main integrated assessment models used in the IPCC Working Group 3. However, what you don't see here is that the social side of the things, demand side mitigation options, and behavior changes. So, so this representation of behavior changes and human systems was considered one of the main weaknesses of the integrated assessment models. And in the choice project, we primarily aim to cover, address this weakness. So choice mainly makes use of 3 models: GloBiome, agriculture and land use model of EASA; Fable calculator, which is a relatively simple calculator for food and land use systems; and the Felix model, that's a global systems model that covers not only food and land use, but many different systems. So with that, I have to emphasize that choice has been a project focused specifically on the food systems. And I think one aspect that distinguishes choice from many modeling projects is the focus on stakeholder engagement and interactive development alongside modeling, meaning that we have several pilots where we collect information from users, from consumers, to be able to represent them in the integrated assessment models. But we also have many activities where we try to share the modeling results together with modeling results with consumers and stakeholders. For that, for instance, we are developing interactive simulation environments for the Felix model that I will tell in a minute. Or similarly, we are developing an interactive environment for the Fable calculator. And we have quite emphasis on immersive tools such as digital storytelling or campaigns with different retailers about sharing the project results and informing them together based on the modeling results. So let me start with the GloBiome model of EASA. This is a very actually old and specific model used by specifically not only global policymakers like the United Nations, but also by European decision makers in DG Agriculture and DG Klima. So GloBiome is a partial equilibrium model. It's an optimization model that finds the cost optimal allocation between the food demand and the food supply. However, there is a very complex process that creates this equilibrium. So it's not only the food market and trade, but also the crop development, livestock development, bioenergy, and forest module. Therefore, GloBiome actually combines multiple specific models, for instance, G4M for forest module or EPIC for the crop yields, depending on several geochemical factors. And it's a highly detailed, disaggregate, highly detailed model. What GloBiome was lacking until now, though, was a detailed heterogeneous representation of consumers. So food demand was one aggregate variable depending on the socioeconomic assumptions that come from SSP scenarios. So my colleague Marta Koziczka from EASA is doing a great work in disaggregating the consumer representation in the GloBiome. So and for that she uses many global data sets on consumption. So currently she has developed a regional as well as age and gender dependent representation of food demand in GloBiome. So with that, for instance, you can see what meat consumption is for each age group coming from each region. And similarly, you can see how it will develop under different scenarios. So this heterogeneity of demand is one improvement we bring for representing behavior changes and human systems better in integrated assessment models. And as I said, GloBiome is a detailed model. With that, consumer heterogeneity will also be reflected in the detailed analysis of land use changes and land use change emissions. Very quickly about the Fable calculator. Similarly, Fable calculator focuses on food and land use. However, it's an Excel-based tool developed by a UN SDSN, Sustainable Development Solutions Network, and it is developed especially for participatory scenario development. With this simple tool, several stakeholders, several representatives can, for instance, decide on food and land use scenarios, like how much the demand and waste will be reduced, or how much the livestock feed is going to change, etc. Then they can immediately test the implications of these assumptions, these scenarios, specifically for their own country. So in that sense, it's quite accessible, and it provides custom results for specific countries interested in that. Within the Choice project, the Fable calculator is better linked with downscale climate projections. And also it's linked to specific pilot-specific campaigns we have in the project from Spain, South Africa, and Colombia. And also the simplicity really helps to develop online training material or serious games or interfaces for the Fable calculator. So for further information, please contact my colleague Clara Duzal from UNSDSN. So now I come to the Felix model. This is my hammer. I have been leading the development and use of the Felix Global System Dynamics model at EASA. But Felix is not a new model. So it was developed more than 15 years ago, initially in a project about supporting global Earth observations. And since then, we have used it for several projects and several peer-reviewed publications about climate change mitigation solutions and sustainability. So you heard a lot about WILIAM. It's a system dynamics model. Similarly, Felix is a system dynamics model. Therefore, it's descriptive and time continuous. Descriptive is a very important distinction there. So it doesn't assume cost optimality or profit maximization in the markets. It just describes the developments as it is. It has been a global model, but recently it has been regionalized for 5 UNEP regions, and you can reach all the documentation and the model file on GitHub. If I say a bit more about the content very briefly, again, you heard about the contents of an integrated assessment model with different components of the biophysical systems, such as climate and carbon cycle, but also socioeconomic sectors such as energy, land use, water. Also social systems. I must say my main interest is improving the representation of humans in climate policy models, in integrated assessment models. Therefore, Felix has a relatively good representation of social systems, demographic change, behavior changes, specifically in the diet change model, education sectors, and also other social indicators for malnutrition, poverty, and well-being. Specifically represented by an indicator called Years of Good Life. And I mentioned GloBiome, for instance, one of the very detailed models for food and agriculture. Felix is a relatively simple model, both in terms of the techno-economic detail and the geographic coverage. And the value of simple models is their help in computational efficiency, their help in simplicity of use, and their help in transparency. So with that, simple models can actually be quite complementary to detailed models used in techno-economic policy analysis, either to swipe through the uncertainties, run different computational analysis, or for flexible model extension, and for engaging stakeholders, for facilitating stakeholder participation in the model building and model use process. So with regards to this last point about facilitating stakeholder participation, in the CHOICE project, we are developing an interactive simulation environment for the Felix model. So with that, you can on-site immediately run the model by yourself by changing the inputs, and you can explore different outputs. In terms of the scenarios, we are focusing on the different behavior change scenarios because this is our focus. You might have seen many climate policy simulators online or offline. So what distinguishes Felix ISE from them is the focus on the behavior change scenarios. So I meant to show a demo, but due to time constraints, I'm going to skip this. So if you are interested, please go to this link you see on the screen. And let us know if you have any questions or comments or any feedback. The other contribution of the Felix model is to the CHOICE project is the explicit representation of behavior changes with the individual social and structural drivers of behavior change. When we talk about a behavior change, often this is represented in integrated assessment models like an aggregate demand measure. In scenarios, for instance, people run what happens to follow emissions if the red meat demand is reduced to half of what it is currently. So that's quite an aggregate representation. Behind this number, there are billions of people who need to change their everyday life. So what we try to represent in this Felix model is the drivers of this change. For instance, social drivers like social norm impact or psychological drivers like risk perception. And based on this, we model the population dynamics, like how many people will choose a particular behavior option. And from then we drive the demand projections. So in this case, in this very detailed figure, you basically see the food demand for different age groups and gender for different consumer groups, like the ones who follow a conventional diet or the ones that follow an alternative diet, like a flexitarian, vegetarian, or vegan diet. And from then we can also get the aggregate global average food demand that can be used in the GloBIOM model that links the two models in the project. Yeah, I will very briefly tell another contribution. So there are different approaches to model behavior changes in integrated assessment models. One of them is to focus on specific behavior like dietary change, waste, or transport mode choice. Another one is to focus on lifestyles, and that's a relatively new approach actually, but it covers the, it's an umbrella term that covers the population dynamics of people who choose a certain type of behavior. For instance, if you have an environmental friendly lifestyle, you would both choose a low carbon transport option and you would probably choose a low carbon diet. So the purpose is to cover those multiple behavior changes, not a single one, but the multiple ones simultaneously. And for this, we are using a lifestyle categorization developed by colleagues Hazel Pettifer and Charlie Wilson at University of Oxford. They, based on survey data from multiple countries, they identified 4 categories of lifestyles like resourceful, active, constrained, cautious. Resourceful, for instance, refers to people who have high low carbon cognition, so who care about the environment, but also have the means, have the resources to act on it. We try to model the drivers of these population changes, categorization changes among these 4 groups, and how their cognitions and behavior change to create the food and energy demand. So what you see is the results of my colleague Deepti Swami's work on modeling lifestyles. So under different scenarios that align with SSP2, SSP1, and SSP3, you see that the fraction of resourceful people in the population will be increasing, especially in optimistic conditions where you assume no climate damage and GDP increase. Similarly, constrained people who do not have the means to develop low carbon actions will be decreasing. So this is our current work in progress, and we will be sharing the results in the coming months. To sum up, in the CHOICE project, as I said, we use different models that are complementary, that have different strengths. For instance, Globalium has a wonderful techno-economic representation that allows detailed analysis. Or Fable has a relatively simple tool that allows country-level participatory scenario development. Or we have the Felix model that has a more complete coupling of human and Earth system feedbacks by representing human systems and social dynamics. So this was an overview of our work. If you are interested more, please don't hesitate to get in touch. Thank you very much.
Thank you very much, Sibel. Also for keeping it really short. Again, sorry for being delay, but thank you to all the speakers first. We can have a brief Q&A session actually, because there are just 2 questions in the chat. And then Christina is also showing a slide with a QR code of a survey that we would like all the attendees to take, so that we can have a feedback on the webinar. So the first question is about forecasts that are made by air quality physiochemical models. They are usually validated with in situ measurements. So is there an equivalent when dealing with integrated assessment models instead? I don't know if Inigo, you want to answer this?
Okay. Well, I think it's a question about how to validate the model, no? In general.
Exactly. Yeah.
Yeah, so I can give a general answer. One of the criticisms of the IAMs, traditional criticism, has been that, for example, when you compare with the validation procedures in Earth system models, no, which in IPCC framework is the working group 1, and in integration models is more working group 3, the validation procedures are very weak and often I would say publicly not existent. So maybe probably there are internal procedures, but there is not an emphasis on validation. So this is in general the field. Maybe some models are doing a better effort, or other modeling teams less. So this is my general answer. I don't know if this person is present and want to reply, or maybe help with the information he or she needs.
And also just a follow-up, I mean, there is a way to evaluate past scenarios with the real-world data. Is it something that's done?
Not so much. Not so much. It's, I mean, I understand that you take the model. For example, if the model starts to run in 2000, then you compare the data, the results, simulation results with historical data. Not so much. I think this is also related with the optimization approach. Many models are calibrated only for 1 year, which is a very recent year. Depending on the available data, and then they optimize. So it's not so much in the tradition of simulation. For example, I can explain that in Medea's model, which is a system dynamic simulation model, we did extensive validation analysis. No, that was chapter of a thesis of a colleague. So we did it, and it's possible, but it has difficulties and also related with the methods of the models.
Okay, thank you. I also activated the microphone of Orestes if he wants to say something more on this.
Yes, thank you. Thank you for your response. I come from another world, the physicochemical Earth system world. So, you know, this is very nice introduction for me, but I have some, you know, I'm trying to understand a bit how it works underneath. Thank you.
You are welcome.
I'm from the CHOICE project, by the way. Yes, sorry. I came from the CHOICE project. I saw the door and entered. Thank you.
Thank you. And also, you had a follow-up question which was related on how disruptive technologies are incorporated.
Yes, basically I showed how, for example, one technology, hydrogen, yes, there is this autonomous module, but it connects with other modules as well. I'm wondering how, internet began in the late 90s. I suppose it enters in all modules or almost all modules, from smart agriculture to commuting to working practice around the world, logistics, whatever. So I'm wondering how you handle these big things.
So it depends also on what do you mean by disruptive. So because here I can understand disruptive in two ways. For example, one way is in the future there will be technologies that today we even don't imagine, no? So because internet was not foreseen, I don't know, 40 years ago, no? So of course this is impossible from my point of view that the models can foresee the future. This is not the purpose of the models, no? But if we have something that is already happening, and you give the example of internet, or now we are studying hydrogen, then we can, with the information available, we can try to do some risk analysis or impact analysis and so on. And I think this is the purpose of these models, because the idea is to try to anticipate potential problems or potential issues, or to try to recommend how deployment of a specific technology could be better done. No, this is, I think, the purpose of modeling, that you can try in your computer before trying in the reality. No, so at least to detect big problems. In relation to specifically internet, I have not done a review about this in IAMs. I imagine this is embedded in the communication sector. I don't think this is very well or in detail model. I don't think so, because also you have to take into account that these models typically are very big models. There is always a delay also. When something becomes important or relevant or we have data, then it takes years to model. No? So there is always a delay. I don't know if anybody else wants to add anything.
Okay, thank you, Inigo. I don't see any other question in the chat, actually. And we actually finished pretty later than what expected. So I will leave you all to go have lunch. And thank you again for all who attended, and also especially to all the speakers. And just remember to take the survey using the QR code that Christina is showing.
Yes, anyway, an email will follow in the next few days with the webinar recording and the link to the survey for those who cannot fill it out now. So thank you.
Thank you all. Bye.
Thank you. Bye.
Bye-bye.
Bye-bye.
Thank you. Bye.
Nice lunch.
Thank you. Bye.